We've covered the fundamentals of supply chain attacks and how attackers exploit the trust we put in third-party software. In this lesson, we're going to examine one of the most significant supply chain attacks of 2025, a self-replicating malware worm called Shai-Hulud, and you might recognize that name. It's a reference to Dune, where Shai-Hulud referred to the sandworms. Now, this compromised hundreds of packages in the NPM ecosystem. Like I mentioned, Shai-Hulud comes from that science fiction novel Dune, referring to the giant sandworms that burrow through the desert planet Arrakis. Attackers, they choose these names deliberately, and just like those sandworms, this malware burrows through the software ecosystem, spreading from package to package, consuming credentials along the way. They even refer to their second wave as the second coming, showing a flair for theatrics that's become something of a signature. This case study is particularly valuable as it discusses multiple techniques, demonstrating multiple attack techniques like credential harvesting, worm propagation, persistence mechanisms, and destructive capabilities. And this is wrapped into a single highly automated attack. The Shai-Hulud campaign unfolded in two major waves. The first wave hit in mid-September of 2025. Security researchers at Step Security first identified the attack on September 15th, when they discovered a package called the @control tiny color had been compromised. Within days, over 500 NPM packages were infected, and according to Checkpoint Research, the attackers managed to steal approximately $50 million in cryptocurrency using this initial campaign. CISA, the Cybersecurity and Infrastructure Security Agency, issued an official advisory on September 23rd, warning organizations about the attack. This threat was considered very serious, even at the federal level. Now, on November 21st, through the 23rd of 2025, the second wave hit, and they dubbed it Shai-Hulud 2.0, the second coming. This was far more aggressive and sophisticated. In just 48 hours, the attackers compromised hundreds of additional NPM packages, creating over 25,000 malicious GitHub repositories and affected packages with a combined 132 million monthly downloads. Major companies were impacted, including Zapier, PostHog, Postman, ENS Domain, and Async API. They strategically timed the second wave. NPM had announced they would be revoking classic authentication tokens on December 9th in response to the first wave of attacks. So the attackers launched their second wave just before this deadline, trying to squeeze in one more attack while many developers still hadn't migrated to the new, more secure authentication system. Let's talk about how this malware actually gets onto your victim systems. NPM, the node package manager, has something called lifecycle scripts. These are scripts that run automatically at different stages when you install a package. For this discussion, the most relevant ones are pre-install and post-install scripts. In the first wave, Shai-Hulud used post-install scripts, meaning the malicious code ran after a package finished installing. But in version 2.0, the attackers switched to pre-install scripts. And that's a critical evolution because the malicious code now executes before the installation completes. Critically, it runs even if the installation fails or is canceled. So a developer runs npm install, and before they even see the results, and before any security scanning tools can check the installed code, the malware is already executing, bypassing most static analysis tools that only examine code after installation. When Shai-Hulud 2.0 infects a package, it adds two malicious files, setup.bun.js and bun environment.js. It modifies the package JSON to include a pre-install hook that runs setup.bun.js. So the first script downloads and installs the Bun JavaScript runtime, which is a legitimate tool, and then uses Bun to execute the actual malware in bun environment.js. Using Bun instead of Node.js is an evasive technique. Most security monitoring tools are configured to watch for suspicious Node.js behavior. So by switching to a different runtime, the attackers fly under the radar of many detection systems. So the first priority of Shai-Hulud once it starts executing is to steal credentials. The malware uses a multi-pronged approach to gather as many secrets as possible. There is local file system scanning. The malware searches known locations where credentials are commonly stored. This includes files like npmrc, which contain npm authentication tokens, gitconfig, and credential helper caches for GitHub tokens. SSH keys in the SSH directory, and cloud provider credential files like AWS credentials, Google Cloud's application default credentials JSON, and Azure configuration files. Then we have TruffleHog integration. The malware downloads and runs TruffleHog, which is a legitimate open source security tool designed to find secrets in code repositories. TruffleHog is normally used by security teams to audit their own code for accidentally committed credentials. The attackers weaponize this defensive tool for offensive purposes, using it to scan the victim's systems for any secrets that might be embedded in configuration files, environment variables, or source code. And then cloud metadata services. When running in cloud environments, the malware queries the Instance Metadata Service, IMDS, to steal temporary credentials. For AWS, it hits the 169.254.169.254 endpoint. For Google Cloud, it queries the metadata Google internal server. For Azure, it uses the Azure Instance Metadata Service. This works not just on traditional virtual machines, but also on serverless environments like AWS Lambda, Google Cloud Functions, and containerized workloads on ECS or Kubernetes. And cloud secret stores. If the malware obtains cloud credentials, it doesn't just stop. It uses those credentials to access cloud-native secret management services, AWS Secrets Manager, Azure Key Vault, and Google Cloud Secret Manager to steal even more sensitive data. So it shows that these malware developers have a deep understanding of enterprise cloud architecture. Now, their second phase is data exfiltration. After harvesting credentials, the malware has to get that data back to the attackers. Shai-Hulud uses an exfiltration method that blends in with legitimate developer activity. Using stolen GitHub credentials found on the victim's system, the malware creates a new public GitHub repository. Every repository created by the malware has the same description, SHA-1-Hulud, the second coming. This marker serves two purposes. First, it helps the attacker locate all their exfiltration repositories using GitHub's search functionality. Second, it creates a signature that security researchers can use to track the campaign's spread. The stolen credentials are uploaded to these repositories in JSON files with names like Cloud JSON, Contents JSON, Environment JSON, and Truffle Secrets JSON. The data is encoded using double base 64 encoding, which is a simple obfuscation technique. So then they've got cross-victim exfiltration. One of the most insidious aspects of Shai-Hulud 2.0, if the malware cannot find valid GitHub credentials on the current victim's system, it doesn't just give up. Instead, it searches GitHub for other repositories with that SHA-1-Hulud, the second coming description, repositories created by other infected systems. It then attempts to use credentials stolen from other victims to exfiltrate the current victim's data. This means your stolen credentials could be uploaded to a repository belonging to a completely unrelated victim, and this creates a resilient distributed exfiltration network where compromised systems share access with each other. And Wiz research confirmed that this cross-victim exfiltration was actively occurring during the November campaign. Phase 3 are your persistence mechanisms. A sophisticated attack doesn't just steal data and leave. It establishes ways to maintain access even after the initial compromise is discovered. Shai-Hulud 2.0 uses GitHub Actions as its persistence mechanism. Using stolen GitHub tokens, the malware registers the compromised machine as a self-hosted GitHub Actions runner under the name SHA-1-Hulud. It then plants a malicious workflow file at GitHub Workflows Discussion, it's a YAML file, in the victim's repositories. The workflow is configured to run only on self-hosted runners and contains an injection vulnerability that allows the attacker to execute arbitrary commands. From that point on, the attacker can trigger code execution on the infected machine simply by opening a GitHub discussion in the affected repository. This gives them a persistent, stealthy command and control channel that blends in with normal continuous integration, continuous deployment, CI/CD activity. Even if the original malicious package is removed, the attacker maintains the access through this back door. Phase 4 is where we have the worm propagation, so that this is why Shai-Hulud earns that classification of a worm rather than just malware, the worm classification being the subset of malware, a specific type. The entire propagation process is automated. It doesn't require any human intervention from the attackers after initial deployment. When the malware finds NPM credentials on a victim's system, it queries the NPM registry to discover all packages maintained by that developer. And this implementation uses NPM Search API with the maintainer filter to enumerate every package owned by the compromised account. For each discovered package, up to 100 packages per victim, the malware downloads the original package tarball, injects the malicious pre-install hook and payload files, and republishes the modified package as a legitimate update. So the entire workflow is automated and parallelized, maximizing spread while minimizing the window for detection. One compromised developer might maintain 10 packages. Those 10 packages might be dependencies of 100 other projects. And you see the exponential nature of this propagation. When those projects update their dependencies and reinstall, 100 more developers get infected, each potentially maintaining their own packages. And this cascading effect is why the attack was able to compromise hundreds of packages and create over 25,000 malicious repositories in just 2 days. Another feature of Shai-Hulud 2.0 that wasn't in the first one, call it the dead man switch, destructive fallback. The destructive failsafe that GitLab's vulnerability research described as the dead man switch. If the malware cannot successfully exfiltrate data, meaning that it cannot authenticate to GitHub, it can't create a repository and can't find any usable tokens, it doesn't just fail silently. It attempts to destroy the victim's entire home directory. The code securely overwrites and deletes every writable file owned by the current user. And this serves multiple purposes for the attackers. It's punitive. They're punishing if they can't profit from a victim. They're going to cause damage instead. Trick or treat. It destroys forensic evidence that might be used to analyze the attack. And it creates fear. The threat of data destruction might discourage organizations from attempting to block the malware's communication channels. Unit 42 at Palo Alto Networks described this evolution as shifting tactics from purely data theft to punitive sabotage, and it represents an escalation in supply chain attack methodology. So let's think about the scope of this attack. During the Shai-Hulud 2.0 campaign, Datadog Security Labs identified at least 796 unique compromised NPM packages, affecting 1,092 package versions. Wiz Research found that approximately 27% of cloud and code environments they scanned had at least one of the affected packages present. So we know the attack created over 25,000 malicious GitHub repositories across about 350 to 500 unique GitHub users. These repositories contain stolen credentials, including AWS access keys, Google Cloud Service account keys, Azure credentials, Microsoft, and GitHub personal access tokens, NPM authentication tokens, SSH private keys, and API keys for various services. Packages from Zapier, PostHog, Postman, ENS Domain, Async API, and Browserbase were all temporarily compromised. Elastic, the company behind Elasticsearch, disclosed that their CI pipeline ran the malware and had data published to a public GitHub repository, though they said there was no impact on Elastic Cloud or their customers. So major players were involved as victims. The combined monthly downloads of affected packages exceeded 132 million. And this is even though the malicious versions were available for only hours in many cases, the automated nature of the CI/CD pipelines means many organizations pulled and executed the compromised code before it was removed. The key indicators of compromise for people who need to check if their systems were affected, they want to look for file names setup_bun.gs or bun_environment.js in the node module directories. They want to check for GitHub repositories with the description Shai-Hulud, the second coming. Search for self-hosted GitHub runners named Shai-Hulud. Look for Windows workflow files at GitHub Workflows discussion YAML file if you didn't create them. Check your firewall logs for connections to webhook.site domains, and review NPM publish logs for any unexpected package publications. If any of these indicators are found, you can assume the affected system is fully compromised and you need to begin incident response procedures. So there are a few technical aspects security researchers noted. Unit 42 assessed with moderate confidence that the attackers used an LLM, a large language model, an AI, to help write portions of the malicious code. And they based this assessment on the inclusion of helpful comments and even emojis in the bash scripts, which is uncharacteristic of human-written malware, but very common in AI-generated code. It's an early example of attackers leveraging AI tools to accelerate their malware development. They also noted that that the malware is cross-platform, so it includes support for running on Linux, Windows, and Mac OS with appropriate payloads for each operating system, maximizing the potential victim pool. And then also, while the two waves of Shai-Hulud use similar tactics, techniques, and procedures, TTPs, Wiz Research noted differences in payload structure and propagation logic that suggest different threat actors may have even been involved from 1 to 2, or that at least the tooling evolves significantly between those campaigns, and they haven't definitively provided any attribution of who's responsible to the public. And this video that I'm doing, we're 12/26/2025 when I say this, so information can change, of course, after today as far as attribution and additional details. So let's think about defensive measures for attacks like this. Now, or this specific attack, if you suspect exposure, pin your dependencies to known clean versions and roll back to builds before November 21st, 2025. You'll want to rotate and revoke all potentially exposed credentials, NPM tokens, GitHub personal access tokens, SSH keys, and cloud provider credentials. And review GitHub organization for unauthorized repositories, workflows, or self-hosted runners. Also, you want to work on long-term hardening by doing things like using NPM's trusted publishing feature instead of a long-lived token. NPM introduced this specifically in response to attacks like Shai-Hulud. Enforce phishing-resistant multi-factor authentication on all developer accounts, NPM, GitHub, and cloud providers. When configuring MFA, use WebAuthn or hardware security keys rather than TOTP codes. TOTP codes can be phished. Consider disabling or restricting lifecycle scripts. Pre-install and post-install hooks in your CI/CD environments, continuous integration, continuous deployment. It will break some packages, but it eliminates the primary attack vector. Limit outbound network access from build systems to only trusted domains, and use short-lived, narrowly scoped automation tokens rather than long-lived credentials with broad permissions. And SBOM, implement a software bill of materials, a practice of this so you know exactly what dependencies you're using and can quickly identify if any have become compromised. Monitor for unexpected NPM publishes under your organization's packages and set up alerts for new GitHub repository creation in your organization. The Shai-Hulud campaign represents a significant evolution in supply chain attacks, combining multiple attack techniques into a single, highly automated package. Credential harvesting, using both passive file scanning and active tools like Trufflehog. Exfiltration through legitimate platforms like GitHub that blend with normal traffic. Persistence through GitHub action runners and workflows. And worm-like propagation spreading exponentially without attacker intervention. And destructive capabilities as a fallback. So this attack exploited the trust that's inherent in package manager ecosystems. When a developer or a CI system runs npm install, they're implicitly trusting that the packages they depend on have not been compromised. Shai-Hulud weaponizes that trust. So we think about the xzutils backdoor that you examined in your research assignment. While xzutils was a patient, long-term insider attack targeting Linux infrastructure, Shai-Hulud was a rapid automating worm targeting the JavaScript ecosystem. Both are supply chain attacks, but they represent very different attacker approaches and they require different defensive strategies. So as you're continuing in your cybersecurity studies and journey, remember that supply chain attacks are becoming more sophisticated and more common, and that the dependencies we use are only as secure as their maintainers. So we have to build our security posture with that reality in mind.